Okay. Hello, everyone. My name is Rohan, and today me, Smit, and Julie will be discussing the graph realization problem. So, what is a graph realization problem? Well, it's a decision problem in graph theory which can be solved in O(n) squared time. It can be solved by using either the Haval-Hakimi theorem, which is done recursively, or the Erdos-Galai theorem, which tests whether or not the n inequalities are valid. It can also be represented using an adjacency matrix with zeros and ones that correspond to the degree sequence given. Okay, so now I'll be giving a brief review on degree sequences. So there are 4 criteria to consider when evaluating whether or not a degree sequence can represent a graph. If all of these criteria are met, it doesn't necessarily imply that a graph G can be constructed. You would still have to use some sort of algorithm like Haval-Hakimi or another method to break down the degree sequence into a simpler one. However, if one of these criteria isn't satisfied by the degree sequence, then graph G cannot be constructed. So these criteria are: number 1, the sum of the numbers in degree sequence must be even. Number 2, number of odd degree vertices must be even. Number 3, sequence must have a repeated number of length greater than 1. Number 4, total length of sequence must be of minimum length of the first number in the sequence plus 1. Theorem 1.1, also known as the handshaking lemma from our textbook, states that in a graph G, the sum of the degrees is equal to twice the number of edges. Okay, so now I'll be going over some examples of degree sequences that do not satisfy certain conditions. So as you can see, the sum in this degree sequence is 21. And you can also notice that you can use the summation equation where the sum of degree sequences is equal to 2 times the number of edges. Dividing by 2 gives you 10.5, and of course we can't have half an edge in a graph. So we can, just by this, we can see that it's not possible to construct a graph G. We could have also said that since we have a 5, a 1, and a 1, so that means there are 3 vertices with odd degrees. When it has to be even. We can use a website like this one to represent the degree sequence of the following graph. As you can see, I've already attempted to create the degree sequence from the example that I just showed. When I try to connect this vertex to any of the other vertices to create a vertex with degree 4, this one becomes degree 3, which we don't want. And if we connect here, then we don't get any vertex with degree of 0. And if we try to connect to one of these, then we won't get any vertices with degree 1. Okay, now on to example 2. Here we have a degree sequence of 6, 5, 4, 3, 2, 1, and 0. So here the degree sequence is also 21. So we can use the same logic as before and say this criteria is invalid, and so therefore the graph cannot be created. We can also justify it by saying that there's 3 odd degree vertices just like before as well. The sequence must have a repeated number that's greater than 1. As you can see, all 7 of these are different numbers. So therefore this graph cannot be constructed. Okay, so now I will try to replicate this degree sequence from the example that I just went through. As you can see, I only got to 65433 and the problem is we have two vertices of 3. If we try to remove one of these edges from vertex 3, then we end up with two vertices of degree 4, so that can't work. We try to remove a vertex from here, then we'll get two vertices of degree 5, so that can't work either. And if you try to remove a vertex here, we'll get two vertices of degree 3 and two vertices of degree 2, which we do not want. Okay, so now I'd like to hand it over to Smit to discuss the Havel-Hakimi theorem.
Havel-Hakimi theorem. The Havel-Hakimi theorem is very useful when we are given a degree sequence and we want to know whether a graph for that sequence is possible or not. In class, we have looked at the degree sum formula, which we also looked at in the previous slide. But there is another algorithm we can look at, and that is Havel-Hakimi algorithm. So the theorem says that the non-increasing sequence A1, A2, all the way to AN, it can be graphed if and only if the sequence A2 minus 1, A3 minus 1 up to AN is also possible to graph. So in other words, when we are given a sequence, the first thing we want to do is sort the sequence in decreasing order. If the first term is 8, we remove it and then subtract 1 from the 8 following term. And we repeat these steps until we get all zeros at the sequence. So 0 at the end of the sequence means the graph is possible, which means we can graph the following sequence. And if we get the negative numbers at the sequence, that means we cannot graph that sequence. So let's look at few examples to have a better idea. So here we have the sequence 5, 5, 4, 4, 3, 3. This is the same example from the midterm. So the first thing we want to do is we look at the first term, which is 5. So what we want to do is we remove 5 and then we subtract 1 from the next 5 terms. And also one thing before I forget, first we want to see if the sequence is already in the non-increasing order. So in this case it is, so we don't have to sort them. So we remove 5 and we subtract 1 from the next 5 terms. And when we do that, we get 4, 3, 3, 2, 2. Now we repeat the same process again. So we remove 4 and then we subtract 1 from the next 4 terms. So when we do that, we get 2, 2, 1, 1. Again, the same process. We remove 2 and we subtract 1 from the next 2 terms. So then we get 1, 0, 1. So now, as you can see, we have to rearrange the sequence because we have 1, then 0, and then 1. So we need the sequence in non-increasing order. So that means what we can do is we can put 1, then we can bring 1 over, so 1, 1, and 0. And now again we repeat the same process. So we remove 1 and we subtract 1 from the next 1 term. And when we do that, we get 0, 0 at the bottom. So that means the graph is possible and we can graph it. So let's look at another example. So now we have the sequence here 6, 6, 6, 3, 2, 2, 1, 1, 1. So as I said before, the same process. First we remove 6 and subtract 1 from the next 6 terms. So when we do that, we get the following sequence 5, 5, 2, 1, 1, 0, 1, 1. Now, as you can see, that these terms are not in order. So we will have to rearrange them in non-increasing order. So when we do that, we get 5, 5, 2, 1, 1, 1, 1, 0. Now we remove 5 and then we subtract 1 from the next 5 terms since they are already we already arranged them in the non-increasing order. So when we remove 5 and subtract 1, we get 4, 1, 0, 0, 0, 1, 0. Again, they are not in order, so we arrange them. Then we remove 4 and subtract 1 get the sequence as 0 0 -1 -1 0 0. So as you can see, we have two negatives here. So when we get the negative number, the sequence, that means we cannot graph the sequence, and graph is not possible. And we can look at one last example, so we can make it quick this time. So we have the sequence 4 4 1 1 1 1. I think this is also a midterm example. Um, so what we do is we remove 4 and subtract 1 from the next 4 terms. So we get 3 0 0 0 1. They are not in order, so we arrange them in non-increasing order. So we get 3 1 0 0 0. Again, we remove 3 and then we subtract 1 from the next 3 terms. So we get 0 -1 -1 0. And we have the negative numbers. That means the graph for the sequence is not possible. And that is all for the Havel-Hakimi. Julie's going to talk about Erdos-Gallwey theorem next.
I'm going to be talking about the Erdos-Gallwey theorem. The theorem, like the Havel-Hakimi theorem, is another way to solve graph realization problem. It gives necessary and sufficient conditions for a finite sequence of natural numbers to be the degree sequence of a simple graph, and sequence that satisfy this condition is known to be graphic. Erdos-Gallwey theorem, a sequence of non-negative integers d1 greater than or equal to ... greater than or equal to d1 dn can be represented as the degree sequence of a finite simple graph on n vertices if the following two conditions hold. 1, it being even, and 2, by the formula below, holds for every k in where k is greater than or equal to 1 but less than or equal to n. Next, I'm going to be showing a couple examples using the Erdos-Gallwey theorem, and these examples are from our midterm. I'm going to determine which of the following sequences are graphic sequences. So the first sequence right here, 5 4 3 2 1 0. We have to check the first condition, it being if the sum of these sequences add up to being an even number. And as we can see, it comes out to 15 and is odd, therefore is not a graphic sequence. And another example from our midterm, 4 4 1 1 1 1. And we're going to be using the formula up there, checking the first condition as it's even. We're going to move on to using the formula to see if it satisfies the condition. So for k equals 1, at plugging it into the formula, it gives 4 is less than or equal to 1 times 1 minus 1 plus 1 plus 1 plus 1 plus 1 plus 1, which comes out to 4 is less than or equal to 5, which is true and holds for k equals 1. Moving on to for k equals 2, plugging it back into the formula up here, we see 4 plus 4 is less than or equal to 2 times 2 minus 1 plus 1 plus 1 plus 1 plus 1, which comes out to 8 is less than or equal to 6, which is not true, which means it fails to hold for k equals 2. Hence, this example is not a graphic sequence. And our last example, also from our midterm, is going to be 5 5 4 4 3 3. So checking the first condition, it comes out to 24, which is an even number, so we can move on to the formula stated previously as for k equals 1 gives 5 is less than or equal to 1 times 1 minus 1 plus 1 plus 1 plus 1 plus 1, which comes out to 5 is less than or equal to 5, which is true and holds for k equals 1. For k equal 2, it gives 5 plus 5 less than or equal to 2 times 2 minus 1 plus 2 plus 2 plus 2, which comes out to 10, greater than or equal to 10, holds for k equals 2. For k equals 2 being 2 is because 2 is plugged in for minimum di comma k here, where it represents the minimum value, and the minimum value from di and k is 2 right here. And moving on to k3 and k4 and k5, we will see in the next steps that the minimum value for these will be 3, hence 3 will be plugged in instead. As we can see, 5 plus 5 plus 4 is less than or equal to 3 times 3 minus 1 plus 3 plus 3, which comes out to 14, is less than or equal to 15, which is also true. Therefore, holds for k equals 3. Moving on to k equals 4, we get 5 plus 5 plus 4 plus 4 is less than or equal to 4 times 4 minus 1 plus 3 plus 3, which comes out to 18, is less than or equal to 18, and holds for k equals 4. For k equals 5, same thing, 5 plus 5 plus 4 plus 4 plus 3 is less than or equal to 5 times 5 minus 1 plus 3. Comes out to 21, is less than or equal to 23, holds for k equals 5. And lastly, for k equals 6, we get 5 plus 5 plus 4 plus 4 plus 3 plus 3 is less than or equal to 6 times 6 minus 1, which comes out to 24, is less than or equal to 30, which holds for k equals 5. Hence, all conditions are met. This is a graphic sequence. And that concludes our presentation, and these are our references. Thank you.